Thank you very much. So now we would like to start talking about our technology at Qemix and also our researches these days. My name is Matsushita, and I'm the CEO of this company, Qemix. And I would like to introduce to you our company. What kind of company we are? Well, we are a software R&D venture focused on quantum computing. And we were established in 2019, and now we have 20 members, including 14 researchers. So majority of our people are researchers. One of the unique point about our company is that, as you can see at the bottom of the slide, we have been developing FTQC algorithm since our establishment. So we believe that we really believe that the FTQC is the algorithm that we had to develop. And so since the moment of our establishment, we have been working on this. And today I would like to talk about our activity in this area. Now, so we are developing FTQC algorithm, and specifically, we are focusing on the R&D for those three areas. One is quantum chemistry calculation, and the next one is CAE, and also machine learning. Now, in these three domains, we want to develop practical quantum algorithm. And this word practical is especially important. This is something we remember all the time when we work on R&D. And I will come back to this concept many times throughout my presentation. So, in our efforts to develop practical quantum algorithm, the most important key is to identify practical real-world problems to solve. And these are the people who are providing us with the real-world problems. And they're actually working with us in R&D activities, and we are grateful for their collaboration. Now, I would like to talk about the result of our activities at Qemix, but before I do that, let me share with you a different slide, which is this one. This is the roadmap of Quantinuum about their hardware. The reason why we're showing this slide is you see the word error rate. So I would like to base our talk on this error rate here. Now, in the coming 5 years, what kind of quantum computer will come out? This is something we think about here. I would like to think about here. The most important year is 2029. So by 2029, 100 logic qubits and also the error rate of 10 to minus 5, this is expected. And especially this number, 100 logical qubits and also the error rate 10 to minus 5, these are important key figures, key values for us. Because for our algorithm, if we can achieve this kind of performance, some of our FTQC algorithm will run. Therefore, we are assuming that in 2029, we will enter at least early FTQC. On the flip side is, we want to be ready with the algorithm that can run on the eFTQC, such as this. And we have come up with many important challenges, but here there are. First is the summarized at the top, striving for quantum supremacy. And we aim to achieve quantum supremacy in all of the three following areas within the next 5 years. And so I would like to talk about what kind of scheme and what kind of technology we would like to use to achieve this goal. First is the quantum chemistry calculation. FTQC can accelerate this quantum chemistry calculation, we believe. And again, the word practicum is very important. Now, what do we mean by this practical quantum chemistry calculation? Well, actually, this is the real problems that you are actually trying to solve in your day-to-day work in this industry. For example, this is an example you see here. 200, 300, or maybe 500 atoms. This kind of scale of the system to be solved at high speed, at high accuracy, this is something that people want to solve. But unfortunately today, with the early FTQC machines, it will be too big as a problem if you try to solve the whole thing on the FTQC machines. 100 logic qubits cannot hold all these 300 atoms. So, to be realistic, the solution we thought is this: high-performance computer integrated with quantum computing. So more specifically, for the entire problem space, we use the classical computers roughly, solving it. And then for the specific areas, we carve out for quantum computers computing to be applied. Let me share with you more specific flowchart. So this is what we believe to be the scheme for practical quantum chemistry calculation. The blue arrows on the left side, this is HTTP-based process, classical processes. Now on the right side, you see orange arrows. These are based on early these will be running on early FTQC. Now, first on the left side, using our HPC, the classical computing will use DFT, for example, to solve it roughly, and then we extract the more difficult part, the hard part. That's the second part. And especially in the second step, one of our technology is used, which is to understand how we can extract the hard part. And this is actually one of the activity areas for us, and we have accumulated a lot of know-how in this area. And then once the hard part is extracted, then we will bring it to a third step, and we will solve it high speed and at a high speed and high accuracy in the quantum computing. And here, again, we'll be using FTQC algorithm called PITE. This is a quantum probabilistic imaginary time evolution method. This provides the high accuracy and high speed. And then we go to the fourth step, which is the seamless connection to property calculation. For example, excitation energy or absorption spectrum. They will be evaluated, and then they will be directly comparable to the experimental data. And using the quantum computing, we do it at very high accuracy, and we have been developing the underlying technologies. Before we actually calculate the properties, we have to do this response function, and this response function, we have developed an algorithm to solve this response function. We believe that the response function is the best function to be used in this use cases. So as you just saw, for those 4 steps to be realized, what kind of elements are necessary? We actually have been working on all these underlying technologies, and all of them are today present. We have them all. So now that they are ready, from end to end, we are able to calculate this calculation. We are able to do this calculation. And actually, we use this actual device to do this test. And we actually worked with Honda for this activity. On the left side, you see Honda's real problem. This is the ZAF spectrum from a battery material. This is X-ray absorption spectrum. The reason why we chose this ZAF spectrum as a problem is because the electron coefficient has to be considered very accurately, and this is condensed matter property, and the HPC cannot do it very well. So for this target, we use the Quantinuum H11 as hardware, and especially this time, Azure Quantum, via Azure Quantum, we use their hardware. And the reason why we chose Quantium's hardware is we are able to conduct mid-circuit measurement, and also there's high fidelity, and also there's all-to-all connectivity. And today, their hardware satisfies all those three requirements, which is our specifications. And because of these reasons, we chose the H1 series from Quantium. Now, even if the hardware has very high specifications today, this is still a NISC hardware. So today, as of today, using today's NISC hardware, we have to change somehow, make it into FTQC with some kind of technique. And for that purpose, we developed this quantum error detection. We actually use, quantum error detection. By realize this PITE which we talked about, which is the FTQC algorithm. And we were able to perform the first ever physical quantity calculation directly. And we conducted the Gauss spectrum calculation. Now, there's another point I would like to mention. Now, it's not a simple problem to solve, which can be just solved by just putting together different techniques. We had to develop more technology, more functionalities, like required number of physical qubits had to be brought down from 56 to down, or the gate operations required to be brought down to 1/12. So all those things had to be solved before the whole thing was integrated. And regarding this contents of the presentation, we'll be presenting this to you in this room in the morning tomorrow. So I do hope that you will come back to this room. I'm sorry, 14:05 in the afternoon. Sorry, we will be presenting this idea for you in this room with Honda. And next is the practical chemical quantum chemistry calculation scheme, as I have shown earlier. So we have all the underlying technology here. So using this, we would like to aim for quantum supremacy in 5 years. And we are looking for more use cases and collaborative research. So if you're interested, let's talk. Next is the second topic, which is the CAE calculation using the quantum computing, FTQC. Again, in quantum computing, CAEs are collecting a lot of attention.
And the reason is, as you can see right in the middle, in quantum computing, this CA calculation basically speeds up exponentially, so it's very, very fast. And so that is why this is receiving a lot of attention. However, but if you want to do a truly practical CAE calculation, it's not here that's most challenging. It's the input and it's the readouts that's very difficult. So these are the two from the beginning and also at the end. Those are the most challenging. So specifically, in terms of input, first of all, we need to input the initial data. And how can we convert that data easily? And the readout, how do we do that? These are extremely difficult. So we have, in order to realize practical CAE calculation for input and readouts, we believe that the answer is HPC and FTQC hybrid computing. So let me start with the input. Even though it's challenging, it's an area that you can build a strategy. Even at Quemix, against different input, we have converted it so that it's actually encodable using a classical computer and input it into a quantum computer. We have developed that technology. However, the real problem is the readout. How can we efficiently read out the quantum status or state? This is the missing piece that's been searched around the world. No one at this point in time has a specific answer to this. This is probably the biggest challenge in utilizing quantum computers. So let me explain a little bit more about this readout condition. So once you're done with the quantum CAE calculation, the quantum bit looks like this. This is the readout result. It's full screen, enormous amount of information remaining on the bit. So if you want to read this out, and if you try to access this quantum bit, in just a moment, a vast information disappears with just a single pixel of information remaining. And this is called the wave function collapse. It's actually a very well-known problem. So you access the readout, and if you want to see what the result was, basically, without this effective readout, the best part of the quantum computing is lost. So without the effective readout, quantum CAE calculations are impossible. So what can we do? This has been one of the major challenges that we have really struggled with. But with the collaborative research with Honda, we have been able to launch new technology for the first time in the world. So if you do a readout, there's a wave function collapse. So what can we do to do a readout without doing the readout? This is what we were thinking as we developed this new technology. What's important here is the input and the readout. With the three, we have all the necessary technological components that are necessary. So next year, we will be able to execute this end to end. I think at least we will enter that phase. Again, with the readouts, we have a session together with Honda tomorrow. So from 4:05 tomorrow in this room, in the keynote room. If you're interested, please come in and listen to us. So these are the three elements that are in place. I didn't emphasize this too much today, but in terms of the quantum calculation, PITE, I want to mention a little bit. Why is it that we emphasize PITE? Because PITE is extremely effective in FTQC era, and it's an outstanding choice as well. Using PITE, when we did a calculation, in terms of the system size dependence, we have seen exponential speed up. So it's a great algorithm, a powerful tool in order to calculate an enormous amount of data. And the necessary qubits is very limited, it's fewer. So it's actually very applicable to FTQC. But in terms of algorithm, QLCA, it's polynomial speed. In terms of number of qubits, we know it's already many. And so this is an algorithm for FTQC. So we have PITE and readouts. And with these two, we will aim to realize quantum supremacy in 5 years. And we're seeking use cases and collaborative research. So if you're interested, please approach us. So let's go to the third topic, machine learning. Again, what is the practical machine learning scheme? So this is where we struggled with at the beginning, because one of the reasons why machine learning is receiving so much attention is because we have in this world today, the model becomes extremely complex, whether it be computer vision or LLM, and this increases energy consumption significantly. And how can we continue to develop generative AI? So that's the big challenge. And now the quantum ML approach is receiving a lot of attention these days. But that approach is basically replacing the entire ML models with the quantum models. But however, this is QNN, and this is probably a representative example. But in this approach, we have this issue of barren plateau, which makes it difficult to scale the quantum ML models. So if you want to scale it to a bigger problem, then it becomes very difficult. So this is probably not a practical machine learning. So this is where we decided to tackle the issue. Again, we believe that HPC, FTQC, hybrid computing is the answer to practical machine learning scheme. One of the major features is that as an AI model, we would basically adopt conventional AI model. So this is HPC, classical computer. We would adopt it as it is. But in the conventional AI model, there's a multi-head attention. This is where the greatest energy consumption takes place, like multi-head attention. We have decided to quantum accelerate this. And if we're able to accelerate this, we would input this in classical AI model, and then we would just continue to run this AI loop. And we have developed a generalized transformation technique. We call it GT technique to accelerate feature extraction on the quantum computers. So I will elaborate on GT. So this is the scheme for GT. To the left, this is the conventional AI model, feature extraction of the conventional AI. So in the current AI, you have Fourier, cosine, wavelet, and then neural network. You would have to basically slice out or just take that out and extract that feature. But what we are proposing is GT. So in each of the conversion, we would multiply a weight called P, and we would basically mix it, all of it. And by mixing it, we would be able to generalize the transformation. Therefore, we would be able to extract a lot of features. And we have actually checked the GT, high feature extraction capacity, on the right-hand side. This is imaging processing using GT. So this is the RegNet 50. This is the ML AI model. And we have basically replaced the feature extraction with our GT. And just with that, you can see that the accuracy has increased from 72.1 to 776.9. So this is 76.9. And if you could look at the orange line, this is the energy consumption. Again, and it's calculating the cost of energy consumption. You can see that it hasn't really changed much from 1.1 to 4.2. And again, one that's using the channel attention is probably the greatest in terms of accuracy, but the energy consumption uses 4 times more. So GT is extremely capable in terms of feature extraction at a shorter speed, at a higher speed. So this is a quantum GT. It has a great affinity with a quantum feature, because if you convert quantum Fourier, you can realize higher speed conversion. And by using quantum computer, you will be able to accelerate the conversion. And on the quantum computer, you'll be able to combine it with GT and get a great result. And this is a preliminary result, but on a simulator, we have run this, and you can see that we were able to train quantum GT without barren plateau, which demonstrates the scalability. So this scheme, which combines GT, is the practical quantum ML scheme. And all the necessary technological components are in place. So we are now seeking use cases and collaborative research. And we want to apply this for practical use. So this is what we have discussed about the 3 areas of quantum supremacy, which we would like to achieve in over the next 5 years. And we're seeking use cases and collaborative research. And we also have a booth, so if you're interested, please visit our booth. So thank you very much for listening all the way to the end.